So only a few more days to the IB physics exam, and this is your emergency video. If you're really panicking about what you're going to do when you sit down for that paper, I'm here to help. I'm going to talk you through the formula booklet. This is your Bible. If you can understand the formula booklet, then you can get so many more marks which you didn't think you'd be able to get. So we're going to go through it step by step. I'm going to hold your hand all the way through it. By the end of this video, you're going to be a lot more confident going into that exam. So let's begin. So I want to jump in here and say that I don't want you to watch this video passively. I want you to watch it actively. I want you to get out your formula booklet, and as I'm talking through it, I want you to make as many annotations as you can. Label what all of the different letters stand for, and write down when the different equations can be applied, in what situations. If you know those two things, then you are so much closer to answering all of the questions in your exam. So first page we're going to look at is the mathematical equations. You might have just skipped by this normally, but it's got so many useful things. For a start, we've got how to divide up a component vector. Whenever you're dealing with things like momentum or force or velocity, sometimes you've got to do it in 2 dimensions. You've got to use a bit of SOHCAHTOA, a bit of trigonometry. Well, you don't really have to think about it because it's all here for you. If you can draw the arrow, which you have to represent, and you have to separate that into vertical and horizontal components, you've got the formulas to do that right here. Next, we've got some trigonometric relationships. We're not going to worry about them. That's like the grade 7 stuff. Not so important. But what we should be aware of is we've got all these different formulas for different shapes. Doesn't come up an awful lot, but it's important to know it's there. The key one, which does come up quite a lot, let's say 3. Area of a triangle, a circle, you know them. But then the volume of a sphere. Spheres come up more than you'd think. And that's stuff like Stokes' law, a sphere which is rolling, it happens. So let's move on. Uncertainties, they make a lot less appearances than they used to with the new syllabus, so we're not really going to prioritize them. In terms of the amount of revision you want to give them, all you really need to know is the difference between relative uncertainty and absolute uncertainty. Relative uncertainty means it's like a percentage or like a fractional uncertainty compared to some value measuring. An absolute means that it's got a unit to it. So I might say my speed has a measurement of 20 meters per second. My absolute uncertainty in that is 2 meters per second, but my relative uncertainty in that is 0.1 or 10% or 1/10. They all mean the same thing, it's all relative. So absolute uncertainty is your just a delta y or delta something, and relative uncertainty is when we make a fraction of it and we compare it to its original value, so like delta y over y. That's probably going to be enough to get you through this section. After that, you're just looking at those formulas, applying absolute where you see the delta y on its own, and relative where you see the delta something over something. Right, the fundamental constants. We are going to spend a tiny bit of time on this because it's worth thinking about. First of all, the one you use most is right at the top, how handy. Acceleration due to gravity, due to free fall. This can also be thought of as our gravitational field strength. That comes up, I think it's in topic D. We're not going to worry too much about it. Let's look at the main ones, which are going to come up. Speed of light in a vacuum, which is C. And confusingly, IB love the letter C when all physicists do. Physicists like to use letters over and over again for different things, just to confuse you. It's just to get you. But we can't help that. That's the way physicists do it. We have to deal with it. So C is also used for the critical angle in refractive index. it's also used for heat capacity. It's a bit tricky, but here we're using it for the speed of light in a vacuum, and that's not just visible light, and this is the key thing I want to get to you. It's also radio waves, microwaves, gamma rays, anything in that electromagnetic spectrum travels at that speed in a vacuum or in air. It's pretty much the same anyway, close enough that we can say it's the same. Then we've got Planck's constant, nice and easy. Elementary charge, that's important. That is the charge of a positron. Sorry, positron, when it is a charge of a positron actually. Also, if we put a negative sign in front of it, it's the charge of an electron. If we keep it positive, it's a charge of a proton. You might have seen this in GCSE as being +1 or -1, but that was in relative atomic charge units, so just comparing them to each other. Now we're given it real units, we're given it coulombs, which is the units we use for all charge, and it's an incredibly small number. 1.6 times 10 to the -19. And then we've got a load of masses of these different subatomic particles. And one key thing which I want you to notice about this is the mass of a proton, mass of a neutron, and the unified atomic mass unit. They're all almost exactly the same. Like 1.6 something times 10 to the -27. That's because we're all very, very similar. And the only time when we really need to know the difference, when you need to pick them out, is when we are trying to calculate the energy transfer when we use Einstein's equation equals mc², when we're transferring matter directly into energy. Then those tiny little mass differences become very important because we use them to create photons of very high energies. Quite often you can get away with just using the unified atomic mass unit, say if you wanted to calculate the momentum of a alpha particle. You don't need to know its mass to that much precision, so I would just do the mass of a alpha particle, which is a helium nucleus. It's got 2 protons, 2 neutrons. The unified atomic mass unit is kind of the average between a proton and a neutron in a nucleus, so I would just use that times by 4. So after that, stuff comes up, but not as much as those ones we've looked at. Next, we've got these metric multipliers. This is so handy. You didn't always have such nice things like this. But say I get given a unit, 10 picometers, and I'm like, what on earth is a picometer? Oh, I don't want to do any hard maths. I'm just going to look at my formula booklet. I've got 10 picometers, so 10, and then look up pico on this table. 10, okay, pico, that is times 10 to the -12. So instead of writing picometers, PM, I would just write 10 times 10 to the -12. I'm just writing 10 to the -12 instead of pico meters. And that's all we have to do. That's all these prefixes mean, is just one of these values times by one of those values. And we don't even have to think about it. We don't have to memorize anything. And the less you have to memorize now, the better. Right, then we've got these unit conversions. I am going to say that the most important one is probably going to be this radians. We need to know it's there. Temperature is also going to be a bit important. These light years, parsecs, astronomical units, we don't use them too much, but they come up a bit when we talk about these grand scales of galaxies, stars, planets, universes, but nothing too much to be worried about. Right. Then we're moving on to electric circuit symbols. This is handy just to know it's here, but more importantly is the electromagnetic spectrum at the bottom. Quite often it's important to know whether one photon or one ray has a higher frequency or a longer wavelength than another one, and you used to have to remember that, but now you don't have to. It's all given to you. So if I wanted to know which had the highest wavelength, gamma rays or X-rays, I could look down here. I could say, oh, there's gamma rays, there's X-rays, and I have my wavelength up, and it's really big at that end and really small at this end. So that means that gamma rays have a smaller wavelength. And I can even get an estimate of the wavelength of a gamma ray if I wanted to. Even better than that, and this comes up more than you think, they tell you a good estimate for the wavelength of visible light. And we can see quite obviously here that blue has a lower wavelength than red, but a higher energy, because energies go in this direction. That is useful when it comes to redshift. It's useful when it comes to a lot of different questions in topic C, I believe it is. So we know that's there. That's all preparing us for lots of different questions we'll be asked. Now we're going to get into the equations. A1, kinematic equations. Your teacher might have called these Suvat equations. And that's because we've got these different variables which spell Suvat. S stands for displacement. I don't think I'm going to write all these out. I'm just going to say them for you. U is initial velocity. V is final velocity. A is acceleration. And T is time taken. Now, what you need to know about all the equations in your formula booklet is when you can apply them. These equations only work for constant acceleration. Sometimes acceleration changes, but in most situations it's pretty constant. If I drop my pen, it's under the acceleration due to gravity. And if we ignore air resistance, then there's no forces opposing it, so we've just got that one constant force of gravity pulling it down, which means we've got a nice constant acceleration. And that's where projectiles come in. When we do projectiles, we have our acceleration is equal to gravity, and we keep that constant, and these equations work really well for that. But here's where students get confused and they slip up. When we talk about our acceleration, it's a vector. It's got to have direction, and that's true for all of these here, except for time. They need direction. My pen falls down, so I'm going to call that direction downwards negative. If it went up, it would be positive. So gravity would be negative. Another top tip for projectiles is I've written all of these letters here. If I'm doing projectiles in 2 dimensions, so I've got a y direction and an x direction, my vertical and my horizontal, I want to think of them separately, but I'm going to use the same letters to represent them. I'm going to use S, U, V, A, and T. So I want to use subscripts. If I'm talking about my displacement in the x direction, I add a subscript. If I'm talking about my initial velocity in the y direction, I add a subscript. These subscripts are to stop me making mistakes, and they'll stop you making mistakes as well. The most confusing thing in the world is when you try to answer a problem and you've got one u over here, which is different to the u over there, and you make mistakes. I'm here to stop you making those mistakes. So let's look at the next set of formulas in A2. So we've got the force of friction, and this is the only equation in the formula booklet which isn't quite an equation. We've got this weird is less than or equal to sign, and we have to understand what that means. So we've got our frictional force is less than or equal to the coefficient of static friction times by the normal force. So I am going to sketch out what this might look like. We've got a box on a plane. This box is weighed down by its weight. I'm going to call that mg. And it is not moving. There is some force acting on it, which is the friction. That is going against the direction which it would move, which is down the plane. So we'll call that F with a subscript F. I love subscripts. You should get into subscripts. They're really good. But then there's also got to be another force when that block is pressing down into the plane that it's on. The weight of that block will press into the plane, and that plane is going to supply a equal and opposite force, which will be the normal force. Sometimes this also gets called the reaction force, and the direction of it is key. The direction is always at 90 degrees to the plane. So it's at 90 degrees to the plane which it's sat on. Now, I'm looking at that and I think I've done an okay job at drawing that. It's not great, those arrows aren't really sized right. They should be making a complete polygon if I drew them tail to tip. So really my normal should be a tiny bit bigger. Let's do that a tiny bit bigger, and then I think I'll be happy with it. And that's because if I redrew those arrows, so tip to tail, so I'll draw my weight, about the same size, followed by my frictional force, followed by my normal, then they should all make a complete triangle. And this is because the forces are balanced. If they didn't make a complete triangle, then I'd be left with a resultant force. That's the sum of all the forces. At the moment, my resultant force is 0, and I know that because it's not moving, which means that at a constant velocity, a velocity of 0, and Newton's laws tell us that if it's at a constant velocity, the resultant force must be 0. And in this case, the resultant force must be 0 because we're talking about static friction. Now, let's look at that weird little less than or equal sign. This is saying that our frictional force has to be less than or equal to the normal force times by the coefficient of static friction. What this is basically saying is that my frictional force can vary when it's static. There comes a point when these become equal. If in this example, if I was to keep tipping my board up and up and up and up, if you can imagine, as I tip it up and up and up and up, there's more force pulling it down, which means there's going to be more there's going to be more frictional force to hold it back. And the point just before it starts moving, these are going to be equal. But only just before. And this is when we see all of our problems in the IB. It'll say at the point when the block just starts to move. And then this doesn't become a less than or equal sign, it just becomes an equal sign. We don't have this for dynamic friction. Because there's no variation in the amount of friction once it's already moving. So let's look next at a few more of these and get through as many as possible. Next we've got Hooke's law. Hooke was actually a bit of an idol to Isaac Newton. He was a giant of physics until Newton came around and just nobody paid any attention to Hooke since then. But he does have a law named after him, which is quite good. When he first published this law, he published it in Latin, but as an anagram, because he didn't want anybody to use his work to do better science than him. That's how they used to do science. It was all like, oh, I found this out first, you didn't. So maybe he wasn't such a nice lad, but he did come up with this law in Latin, which he said as extension, so the force, that's in English, but he wrote it in Latin in an anagram, which means the force of the spring is directly proportional to its extension. So this is the force of the spring, Fh. X is the extension, X extension. And K is the spring constant. And the spring constant is a measure of how stiff the spring is. The higher the spring constant, the stiffer the spring. And that'll be helpful if you imagine it, because if you imagine trying to pull the spring out and it's really stiff and you can't pull it much, but you're putting lots of force in, you've got a lot of force but not much extension, which means you must have quite a stiff spring, so a high spring constant. The only other thing to note here is the minus sign. And why do we have that minus sign? It's because, again, we've got these vectors. And that must mean that the direction of these vectors is important. So here we're saying that the force from the spring is in the opposite direction of the extension. So if you imagine if I pull my spring, here's my spring, I am going to extend it this way to the right. So the extension has gone like that. Well, what direction from is the force going to be once I've extended it? The force from the spring is going to want to pull it back to the way it was, so that's going in the opposite direction. And that's where we get this minus from. Right, let's get through a few more. We have got next Stokes' law. So it's called Stokes' law, but unfortunately he's not famous enough to get that little subscript, poor lad. We've got a D there instead because it's really all about drag. This is the equation that tells us about the drag a sphere will feel as it falls through a viscous liquid. So I say sphere because it only works for spheres. And that's important because if you ever see a sphere, a ball, falling through a liquid in a question, you're like, Stokes' law, that's drag. I'm probably going to use this somewhere. So I said also through a viscous fluid. Viscous kind of means it's like thick. It doesn't work so well for air because it's not very viscous. We can barely feel air. But something like water, or more commonly oil, sometimes used washing up liquid. Sometimes I've seen like a sugar solution or honey. They're all going to have a viscosity. And viscosity is this weird looking Greek letter, which looks like a N. Now, the more viscous the fluid is, the thicker it is. So the higher that funny looking N is, the more viscosity it's got, and therefore the more drag we're going to feel. Obviously, I said this was also about a sphere, so we've got the radius of the sphere, and then we've got this V, which stands for the velocity which the sphere is moving through that liquid. Now, generally, we're going to be talking about terminal velocity for these experiments. Because once you get a terminal velocity, as I mentioned before, constant velocity means a zero resultant force. And once we've got zero resultant force, then we can do maths a bit easier. And after that, that's all we really need to know about that. Next, we're going to move on to buoyancy. That's what the little b stands for. And the buoyancy, we've got this little Greek letter rho, which is like a funny looking P. It means density. So if we want to consider buoyancy, we have got to consider the volume of the object which is submerged. So I'll tell you how this gets tricky. If we imagine, say, an iceberg normally isn't completely submerged. So if I wanted to consider the volume for this equation, well, I'm only going to consider that part of the volume, the part which is submerged in whatever liquid we're talking about. And that's the only tricky thing you need to know about that equation. Then we've got the equation for weight. Here it's talking about the force due to gravity, but generally we just refer to weight as mg. Not much to that really. We'll move on. P for momentum. Momentum you can think of as how difficult it is to stop something. If something is really massive and you want to try and stop it, it's going to be really hard. If it's moving really fast, it's going to be really hard too. Momentum is conserved always. And this is one of the special properties about it. It really helps physicists solve problems. If you see a question about momentum, you might want to use conservation of momentum to help you solve it. It says that the sum of the momentums before the collision is equal to the sum of the momentums after a collision for a fixed system with no outside inputs. So imagine two things coming together. If we knew the momentum before they came together and after, it should add up to be the same thing. So momentum of this plus momentum of this is equal to momentum of them together afterwards. Next we've got impulse, which is J, because of course it's J. So impulse is, it's just a change of momentum really. I think that's the best way to say it. Yeah, because if we look at this equation just below it, we can rearrange the left hand part and the right hand part. F is equal to change in momentum over change in time. I can take that change in time over to the other side by multiplying both sides by change in time. And I can see that, oh, that's now the same as this. So that must mean that change in momentum is just impulse. So if you forget what this means, you can just look down to the equation below and be like, oh yeah, of course. Impulse is J. That's so obvious. And it means change in momentum. Next, we've got Newton's second law written down in formula. Now, this is helpful in quite a lot of ways, because whenever we talk about resultant force, we're talking about this. And this is what I want to be really super clear about. F does not stand for force. Don't ever kill yourself and think that. F stands for resultant force. It's the sum of all the forces acting on an object. And if you remember that, then you won't make the mistakes that the IB is trying to make you make. You won't fall into their traps. After that, that's pretty simple. Mass, acceleration, change in momentum over change in time. And that'd be change in time while that force is acting. Next, we're going to move on to circular motion. Now, before we discuss the Subat equations, and they were super helpful, I said as long as your acceleration was constant, you could use them. Circular motion is different. It's a different situation. Because when you're in circular motion, your velocity is always changing. When you go from one part to another part of that circle which you're going around, you're changing the direction of your velocity, which is important. Because if you change your velocity, you're changing your acceleration. So you cannot use kinematic equations to help you solve circular motion problems. You've got to use these ones down here. But that's fine, there's plenty there. We've got acceleration, we've got our velocity, we've got our radius, we've got our angular velocity. Now that's using the symbol omega, which we also use for angular frequency. There's not much difference between them. One's a vector, one's a scalar. At this point, it's too late to look into the difference when your exam's a few days later. Let's just not worry about it. Then we've got the radius of your circle. And then we've got the time period for the time taken to complete your orbits. Right, moving on to work, energy and power. So we got this equation for work. Remember, work is just like energy transferred. It's just energy measured in joules. We're taking that super easy. We're not going to make that complicated. Times by force, times by displacement, and times by the angle between those two vectors. So what I mean by that is sometimes our force might be in one direction, but because we're kind of dragging something on the ground, that force doesn't actually move it in that direction. The displacement is actually in a different direction, in which case we need to know the angle between them, and we need to use a cos function to alter the amount of work done. One other thing you need to know about that is if in the handy instance they're both in the same direction, the force and the displacement, well then actually the angle between them would be 0, and cos of 0 is 1, which means we can just kind of forget about it from the whole equation. I know you do this in maths, but it's worth noting, if you can understand roughly what the cos graphs and the sine graphs look like, it's going to actually help out quite a lot in physics, because it can be really helpful to know at which angles these functions are equal to 0 and these functions are equal to 1. Because if we imagine the cos function when it's equal to 0, that's when theta is 90 degrees. So if I have my force and my displacement at 90 degrees to each other, then I won't be making any work done. There'll be no energy transferred. And that might come up in a multiple choice question as a way of kind of trying to trick you. Then we've got kinetic energy. And we've got all these equations, m mass, v velocity, p momentum, and m mass again. Very simple to use these. And I want you to kind of think of these equations for work, energy and power differently to the way we think about forces. When you're going through your exam, if you use energy, it's a way of calculating things and making predictions. But force is not just about calculating things and making predictions, it's also about explaining things. What I mean by that is if you get an explanation question and you can explain it in terms of the forces, we use forces to explain how motion changes. We don't use energy so much to explain things in physics. That's just a general rule. It'll work 90% of the time, but not all the time. Then let's look at what else we got. Gravitational potential energy, nothing too difficult about that. Delta H is change in height. Higher something is, the more energy it has. Then we've got, they've got a little H here for Hooke's law, which means, it's going to be related to springs. We've already seen that. And we've got that X for extension again. So the more you extend a spring, the more energy you store in it. And again, we're using K, which is the spring constant. And again, K is one of those letters that we like to use in physics. It just stands for constant most of the time, but then some specific type of constant. We've also got K for the Boltzmann constant, and I'm sure there's another place it's in there as well. Next we've got power. This is a super useful equation. One of the key things about this equation is we have to realize that that delta W, the change in the work done, can be replaced almost ubiquitously with any type of energy. So we could just say change in energy if we wanted to. It's also equal to force times by velocity in the same direction. So finally, we've got efficiency, which again, we're using that Greek letter for, which we've already used before, just to make it confusing. Efficiency isn't too hard. And it's one of those annoying ones where we don't really use any letters for it, we got words instead. But I suppose that's kind of helpful if you don't know what you're doing. You don't have to remember anything. Whoops, I missed topic B. That's okay. I'm going to do topic B for you now. Whoops, I missed topic B. That's okay. With the magic of editing, I can slip it straight in to the video now. So, we've got rho, again, our Greek letter. Rho stands for density, which is mass divided by volume. This is one of the most basic equations. It's not going to get easier than that for the whole of the IB. Then we have kinetic energy, but it's got this weird kind of hat on it. What does that mean? Well, generally in physics, if you've got a hat on anything, it means the average. So this is actually the average kinetic energy. And it's the average kinetic energy of a particle in a gas. A monatomic particle, an ideal gas, basically. And by monatomic, I mean it's unbonded. It's not like CO2, where you've got three things stuck together. It's like xenon, like a noble gas, which is just one particle existing on its own. It'll tell you in the question it's an ideal gas. Then we've got Boltzmann's constant, again another K. And then we've got temperature, because temperature is actually just directly related to the average kinetic energy of the particles in a gas. That's all temperature in a gas is. It's how fast the particles are moving on average. Then we've got a bit of energy equations. We've got energy supplied, heat energy supplied when we want to raise the temperature of something. So mass, specific heat capacity, and change in temperature. If we want to consider when we're heating things, sometimes when we heat things the temperature changes, sometimes their state changes, and that's the next one. This is the heat energy added when we want to melt or freeze or evaporate something, and instead of using specific heat capacity, we use latent heat capacity. Let's talk a bit about some of those words, because I said specific heat capacity. Specific means per kilo. It's got like a legit meaning in physics. It means per kilo. So if you want to describe specific heat capacity, it's the amount of energy needed to heat up 1 kilogram of a substance by 1 degree Celsius. And then we've got L, which that's got mass in there as well, so that must be specific latent heat capacity. It's the amount of energy required to heat up 1 kilogram. No, not heat up. It's the amount of energy required to melt or change the state of 1 kilogram of a substance. And again, these are like specific to each substance. Right. Then we've got change in heat energy over change in time. That's rate of change of heat transfer. Heat transfer. Oh, look at this, another K. We just have K's everywhere, don't we? So that's a constant. A is going to stand for cross-sectional area, change in temperature, and the distance across which that heat transfer is. I can't remember what K this is. Looking at the equation, we don't have a subscript for that K. I think it's specific to each material. Yeah, I'm happy to say that. And then we've got another L, different to other L's that we've seen. This doesn't stand for length. This time it stands for luminosity, which is kind of how bright something is at its source, because we've got another term called brightness, which is how bright something looks when you're far away from it. So if you're standing really close to a light bulb, it's going to look super, super bright. But like, it's always going to have the same luminosity. It doesn't matter how far away you are from it. So this is luminosity for a black body. And the most common type of black body we see is a star. A black body is something that is a perfect emitter and absorber of radiation. So that means it's not really reflecting anything. But interesting part about this formula is how it's written, which is a bit unusual, and the IB does this. We've got the luminosity, which is L. Again, we've got so many different L's, but this is another one. We've got the Stephan-Boltzmann constant, that's in the front of your formula booklet, you can find that. Then we've got area. Now, typically this formula doesn't always use area because it's almost always talking about a sphere. And that's because stars are spherical. And the thing is, like, in your formula booklet, this is a big shortfall of your formula booklet. It doesn't have the area of a sphere, which is really weird. It has the area of a circle, it has the area of a cylinder, but not a sphere. So if you get given the formula for the area of a sphere, because if you need it, they'll give it to you, then you know automatically that you want to be thinking about luminosity. But they may have left this area in there in case they wanted to use a different shape, like a cylinder. Anyway, it's proportional to temperature to the power of 4. And one thing I should point out, all of these temperatures that we've looked at, they've all got to be in Kelvin. The only time you might get away with it is a change in temperature, because changing temperature between Celsius and Kelvin, it's the same. 1 degree Celsius is the same. A change in 1 degree Celsius is the same as a change of 1 degree Kelvin. It's only the start points which change. Kelvin starts at -273, and Celsius starts at Kelvin starts at 0. Celsius starts at -273. Anyway, there's a formula to convert between them. One, not quite formula, but a conversion metric in your formula booklet. Right here. And let's have a quick look at those areas which are available. As I said, we've got curved surface of a cylinder, area of a circle and a triangle, but generally we'll be dealing with 3D shapes when we talk about a black body. So let's get back into the next one. We've got brightness. Now that's what the B stands for, is brightness, and we've got the same L as just before, luminosity. And then we've got 4 pi d squared, d being the distance which the observer is away, because brightness is all dependent on the observer, how bright it looks to the person who's looking at it. And we could describe this as an inverse square law. If I get twice as far away from the star, it's going to look 4 times as dim, because you've got to square that distance to figure out how much dimmer it's going to be. And if I get 3 times as far away, it's going to be 9 times dimmer. And that can be a bit of a shortcut when you're doing multiple choice questions on brightness. Then we've got something called the peak max wavelength. Now, to understand this, we need to really think about the graph which is behind it. So, essentially, when a black body, so like a star or something that's hot, is emitting radiation, it's not just emitting one wavelength. There's a range of different wavelengths. So if I imagine that range of different wavelengths, it's going to look something like this. It's got this characteristic shape. And let's label these axes. On the x-axis we've got wavelength, and on this axis I think it's intensity, but it's basically the amount which is emitted. And you can see at some point there's a peak in the intensity for a certain wavelength. Well, if you wanted to know what that peak was for any black body, as long as you know the temperature of that black body, then you can find the peak max wavelength. Just using this constant here. Nice and easy. Also, what this tells us is how this graph might change if we change the temperature. So now I'm going to draw a hotter black body on the same graph. And if it's going to be hotter, then our peak wavelength is going to get shorter in order for this equation to make sense. So I am going to draw my peak wavelength being here. Because it's hotter, it's also going to be more intense. And we're going to get a graph that looks like this. Always above. And with a higher intensity of the peak wavelength. But the peak wavelength is actually a shorter wavelength. So let's move on. Let's move on to the greenhouse effect. Now, this is quite tricky, and I've always found it really hard to explain to my students how it works. But if you have a look at my website, fenwicktutoring.com, there's a really good simulation of how the greenhouse effect works. I'll try and get as much into now these equations as I can, but here's a quick peek at what the simulation looks like. And you can fiddle around with all these different things and try to understand how the energy coming in always has to really equal the energy coming out. Anyway, emissivity. So this is a measure of how good a black body something is. Because I've talked about a black body before. I said something that emits as much energy as it absorbs. It's a perfect emitter and absorber. But not everything acts like that. So a black body will have an emissivity of 1. And that's the perfect amount. Sometimes they'll emit a bit less, and we can get lower and lower emissivities all the way down to 0, which is, I guess, theoretically impossible. Maybe theoretically possible. It won't come up. So here with this equation, I don't really like the way that it's written, this power emitted per unit area, because I would write power emitted per unit area as symbols. I'd say power emitted per unit area. Why not write it like that? And then I could sub that into my formula, and I could say that emissivity is equal to power per area over Stefan Boltzmann's constant, temperature to the power of 4. And what I'm going to do is this A here, I can actually just take it down to the bottom of the fraction because it's in the denominator of the numerator. So we'll rub that out and just stick it down there at the bottom. And now I've got myself an equation I can actually use. Now we're going to move on to albedo. Albedo is kind of a measure of how reflective something is. So I don't know, polar bears always come to my mind for this because they're white and they reflect quite a lot of the solar radiation that hits them. I mean, so is the Antarctic. It's really white because it's made of snow. It reflects a lot, so it's going to have a high albedo. And if we look at what it says, it's a total scattered power divided by the total incident power. So scattered is just, you know, kind of a different form of reflection. It just doesn't always go in the same direction. And incident power, incident just means the start. If you ever talk about an incident ray, it's the beginning ray. So this is the power to begin with. So if you've got your sunlight shining down on your polar bear and you want to find its albedo, you need to figure out how much of that incident sunlight, the power we start off with, is scattered / reflected by the polar bear. And again, this is going to be some value. 1 being the greatest and 0 being the lowest. Now, if we think about what 1 means, that 1 means it scatters everything, it reflects everything, so it doesn't absorb any of the heat, any of that sunlight. If we had a albedo of 0, then that would mean that it didn't scatter anything, which means it absorbs everything. Now let's keep in mind that 3 things can happen with this incident rays. It can be absorbed to later be emitted, or it can be reflected / scattered, which just happens in the same instant. And I want you to think of reflecting and scattered, pretty much the same thing. And when we think of absorbing and emitting, they kind of both happen together, but like not necessarily at the same time. And not necessarily the same wavelengths as well when it comes to absorbing and emitting. You might absorb one wavelength and emit a different wavelength, but with scattering, you do reflect exactly the same wavelength. Right, on to our gas laws. And first we've got pressure, which is equal to force divided by area. Right, so I'm going to pause now because we've been going quite a while and tell you a joke, a physics joke, my favorite physics joke. And you can tell all your friends this and they'll hate you for it. So, in heaven, Isaac Newton, Pascal and Einstein are all playing hide and seek. It's Einstein's turn to count. So what he does is he turns around. So it's Einstein's turn to count, while Pascal and Newton, they go hide. So Einstein, he turns around, he counts all the way up to 100, and he looks back and he sees Newton stood right in front of him. And he's like, what's going on here? And he looks again, and Newton, he's actually stood in like a chalk square. He's drawn a chalk square around him. He's like, what is Newton doing? Man, he never gets it. He never gets the games. So he says, Newton, you were supposed to be hiding, and I've already found you. That's not how the game works. And Newton goes, you haven't found 1 Newton. You have found 1 Newton per square meter. You have found Pascal. Right, and if that joke didn't make any sense to you, it's because you need to learn your physics better. Pressure is measured in pascals. The equivalent unit to pascals is newtons per square meter. Now you might get to the situation, and you probably will have this in paper 1A, where you get asked to find the units for something. If you get stuck on units, you can use formulas to help you, and you can find some equivalent units. They may not be the perfect units, but they are correct still. And what I mean by that is, if we know pressure is measured in newtons, pressure is calculated by force per area, we can just use the units for force, newtons, and the units for area, meters squared, and we have a unit for pressure now, which is correct. So, moving on, now we've had our light break, on to moles and amount of stuff. Now, this one always confused me, and I never got around to actually memorizing it. I always have to figure it out. And to figure it out, I always think, well, moles is just like we're trying to make the units easier for ourselves. Instead of dealing with like millions and millions of gas particles, we take a unit which will represent millions and millions of gas particles, and then we'll just be dealing with smaller units like 10 and 20. So, first of all, we've got Avogadro's constant, Na. So let's remind ourselves of what that is. That is 6.02 times 10 to the 23. That's the amount of particles in 1 mole. That's what it represents. That's a ton of particles. So Now what we've got to do is figure out what the other two n's mean, because physicists love confusing formulas. If this is just some massive number, well, the number on top of it, if that was also a massive number and they were similar size, then we'd have similar size fractions one on top of the other, and we'd end up with a much smaller number. So by that leap, I can say that this has to be the bigger of the two n's, which makes sense. It's the capital N, so it's going to be the bigger number. This is going to be the amount of particles in whatever we're measuring, and the lowercase n is going to be a smaller number, which is going to be the amount of moles. So if you had, say, 12 times 10 to the 23 particles in your sample of gas, well, that's the amount of particles, that's n. If we divide that by Na, which is 6.63 times 10 to the 23, we're going to get an answer of approximately 2 moles. And dealing with those kind of numbers like 2 and 3 and 10 and 20 are much easier, and that's why physicists and chemists do this. Actually, I'm blaming chemists for this one. I don't think this is a physicist thing, I think this is a chemist thing. Next, we have the same equation 4 times as effectively. This, however, is one of the most powerful equations in physics. I guess that's why we have it so many times. It's the ideal gas equation. Now, it only works for ideal gases. What do I mean by that? An ideal gas is a monatomic gas. Monatomic, meaning only one particle. One is mono, and atomic, I guess, must be particle. That means that there's no bonds between the particles. That's really important, because if you had something like O2, oxygen, 2 molecules, there's a bond between those molecules. That means it can vibrate and store energy in those vibrations. We don't want to be storing energy anywhere inside our ideal gas except for the speed of the gas. So that's the idea of an ideal gas. All of its energy is contained in the speed of the particles, the kinetic energy of the particles. In a real life, most gases aren't ideal. So we don't just talk about the kinetic energy, we talk about the internal energy, which is the sum of the potential energy from the vibrations and the kinetic energy from its movement. So P, that stands for pressure, V stands for volume, T stands for temperature, and then that's equal to some constant. If I took this equation and rearranged it, I could write P V over T is equal to N times by R, which should tell you really that N times by R is a constant. N is the amount of moles in our gas, and if we're doing any experiment, we're not adding more gas to the experiment. We're keeping a fixed amount of gas, so that's going to stay constant. And R, I believe, is called the gas constant. Again, this gas constant, as well as the Boltzmann constant, are both available in your fundamental constants, here and here. Now, one of them works really well when you have the amount of moles, the other one works really well when you have the amount of particles. And we've just been through what the symbols are for moles and particles. Little n is for moles and big N is for particles. So let's then look at the pressure in the next one. Now, again, we've got P, and again, this is going to be for a gas, and we know that because it's gas laws. Then we've got density, which is going to be the density of our gas, and then we've got V squared, which I believe, is going to be our average velocity of the particles. Now, when we think about the average velocity of the particles, you might be thinking back to, oh, we had something for the kinetic energy. Could that work? I think it potentially could. And we could use that kinetic energy to calculate our velocity of our particles and then find the pressure. So we're on to U now, and U is the internal energy. Now I've mentioned that before. I said the internal energy was the sum of the kinetic energy and the potential energy of the particles. But here we're dealing with an ideal gas, which means there's no potential energy. So we could just think of it as the kinetic energy of the particles. And then that kind of makes sense because it's only really dependent on the temperature. And we know that the temperature of a gas is just a measure of its kinetic energy, i.e. the speed of average speed of the gas molecules. And again, we've got two different ways we can use this. One of them when we have the moles, and one of them when we have the amount of particles. Next, we're moving into current, and current confuses so many students. And that's due to like a fundamental misunderstanding of what these concepts mean. Now, in this video, I don't have a lot of time to go into depth to tell you exactly what current is. I can tell you it's the rate of flow of charge, and that's exactly what this equation says. We've got the rate, that's delta something divided by delta time. That means rate of change. And it's the rate of change of charge, which is Q. The other big thing that comes up in circuits is voltage or potential difference or EMF. Now, I can give you again the quick definition for this, and I'm going to use this equation. Voltage is the amount of work done per unit charge as it travels through a circuit or something. It has to be from one point to another. That's why your voltmeter connects in one place and then another. And the difference between voltage, EMF, and potential difference is voltage is like your umbrella term, and EMF is when we put energy into the circuit, like a battery, and potential difference is when we take energy out of the circuit, like a bulb. So this is another quick tip. If you ever have to define anything and you don't know how to define it, look up the equation in the equation booklet. Use that equation in words for your definition. Then we've got a rearranged form of Ohm's law for resistance, voltage, and current. Very handy. Then we have our old friend rho, which this time doesn't mean density. It means resistivity, which is different to resistance. Resistance is a property, of an object. Resistivity is a property of a material. So if I had a long cylinder, and this is generally how these ones go, because a long cylinder can be like a model for a resistor or a model for a wire. If we know the cross-sectional area and we know the length and we know the resistance of that particular bit of whatever we're measuring, then we can use that to calculate the resistivity. Again, that's a property of a material. It's similar to resistance because it tells us how much a material resists the flow of current. Then we've got all these handy equations for power. And one important thing to remember about power when it comes to explaining things in currents, the amount of thermal power which is lost is dependent on the current, not the voltage. So if you ever have to explain energy transfers and loss of energy in a circuit, it's down to a high current somewhere. And we get high current in lots of different ways I don't have time to get into, sorry guys. Then we've got these series and parallel circuits. It's just what it says on the tin, really. I do have one quick warning for you though, is the IB likes to combine series and parallel. So this type of circuit comes up over and over again. It's probably going to come up in your exam, in one of the two papers at least. Because here we've got one section which is parallel and one section which is series. So here's a parallel, and we call that bit parallel because the current has two different parallel paths that it could travel. And the other part is series. Now, if we consider series and parallel and we want to find the resistance of them, it's very clear that it's harder to find the resistance of stuff in parallel because that equation's annoyingly tricky. So when I see a circuit like this, I'm looking at that parallel bit and I'm thinking, wow, I wish that was series. So much so that I'm going to make it series. I'm just going to imagine that as just one big resistor which is in series with the other resistor. And I'm going to use this formula for RP to imagine the resistance of what that resistor would be if it was just one resistor in series. And once I've done that, I can combine it with the other resistor in series and solve the problem. Other key thing to notice about circuits is the big part of your cell or your battery is positive and the small part is negative. Conventional current always flows from positive to negative. We're not going to get into electron flow today, we do not have time. So I'm just going to keep sticking to the standard level stuff because I do not have time for additional high level. We are now on to simple harmonic motion. Harmonic motion is things moving up and down. It's slightly different to waves because waves you have to transfer energy from one place to another without transferring matter. But simple harmonic motion is just wobbling, so we don't really have that transfer from one place to another. We're going to have a look at this first equation and we're going to imagine it as a graph because I always see it come up as a graph. Essentially, the acceleration of your thing in simple harmonic motion is directly proportional to its displacement. But we've got this negative sign here and this omega squared, which is what I referred to before. It's the angular frequency. Again, the negative sign, it means something. It means that the displacement and the acceleration are always in opposite directions. So if I wanted to graph this, I'm going to imagine it as a straight line graph. My angular frequency will have to be constant. So we know the formula for a straight line is y equals mx plus c. In this case, I have acceleration is equal to negative omega squared x plus 0. So I don't really have to worry about this constant here because the constant is 0. And my gradient, which is m, is given as negative omega squared. It's key that it's negative. And also because I found out that my c was equal to 0, that means it's going to pass through the origin. So if I sketch this graph, it's going to be a negative gradient, and that gradient will be equal to omega squared. And then on my y-axis, I've got acceleration, and on my x-axis, I've got extension. Remember, that is equal to your gradient. So then we've got time period. And this is a very useful one for time period. This relationship between time period and frequency also works for waves. That's quite handy. Angular frequency again, and then we move on to time period specifically for mass on a spring. You're going to recognize that it's for a spring because you've got that K for the spring constant. And the important thing to know here is these are the only things that affect the time period for a mass spring: the mass and the spring constant. If I change other things, like say the gravity of the situation it's in, it does not affect it. Mass and spring constant are not affected by the acceleration due to gravity. So this relationship handily will work in space. And fun fact, this is actually how they measure the weight of astronauts, using this relationship. Then we've got the time period for a pendulum, and the only things that affect the pendulum are the length of the pendulum from the pivot to the center of mass of your bob and the gravity of whatever field it's in. So normally Earth's 9.8. I said the word bob there, that's a scientific term actually. It means the small round sphere that you use for a pendulum. It comes up in exams. The wave equation is super useful. We're talking about v here, the velocity of our wave. If we're talking about electromagnetic waves, then that is going to be the speed of light for any electromagnetic wave, radio waves through to gamma waves. Then we've got frequency, and lambda is wavelength. And then we've also got time period. Nice and easy. And then we'll move on to wave phenomenon. N. Lots of my students struggle to remember what this is. N stands for refractive index. It's a measure of a material, and it's a measure of how much that material slows down light. So a high refractive index means it's going to slow down light quite a lot. A low refractive index means it won't slow down light much compared to the speed of light in a vacuum. So the speed of light in a vacuum actually has a refractive index of 1. You can't get lower than that. That's the lowest possible refractive index. If you got one lower, it would imply that your light was traveling faster than the speed of light in a vacuum, and that's impossible. And then we've got another refractive index, because this equation is all talking about refraction, and that's going from one medium to another one. So that's why it's important, if you draw a diagram of something refracting, that you add arrows. So let's imagine this is glass, which has a high refractive index, and this is air. Air, we say, has the same refractive index as a vacuum because it's close enough. So that's going to be 1. So here the refraction would be away from the normal. And you can figure that out if you find out what these angles are. I am adding some lines here called the normal. The normal is always at 90 degrees to the surface, and we need the normal because we measure our angle of incidence, or theta 1, from it, and our angle of refraction of θ2 from the normal to the ray. Things to watch out for in the IB is sometimes they won't give you that angle, they'll give you this angle instead, and they'll say it's like 70 degrees. And then you'll be tempted to put 70 degrees into the formula, that's not the one you wanted. If you know that the normal is always 90 degrees to the surface, you can figure out that θ1 would be equal to 20. And then you'd be golden. These V2 and V1, they are talking about the speed of the waves in that material. So if that material was air, we could use the speed of light. If it wasn't, it's probably going to be something slower than the speed of light. Right. Continuing on, we've got constructive interference and destructive interference. This is what happens when waves are in phase or out of phase. So if I draw this wave here, and then I draw another wave which actually has a path difference of one wavelength, so basically it's just one wavelength longer. As long as these waves are coherent, meaning they have the same wavelength, that's enough definition for that. Well, the path difference here from here to here is one wavelength. N here stands for any integer number. So I could have that be 2 wavelengths or 3 wavelengths or 4 wavelengths. As long as that's a whole number, this is going to work out. These will be in phase by the time they hit something together, which means we get constructive interference. If, however, I started half a wavelength behind, then the waves would be completely out of phase by the time they hit something. And that is where this comes in, because that's destructive interference. Because they're no longer in phase with each other, they're in antiphase, they cancel each other out. We get destructive interference. And this would happen if I had a path difference of half a wavelength or half a wavelength plus a whole wavelength, which is kind of what we get here, or half a wavelength plus any amount of whole wavelengths. Next we have the double slit equation, and I think this one's super tricky because this is a distance, this is a distance, this is a distance, this is a distance. We've got four distances here, which is annoying because we've got to remember which one's which. So let's start with S. With the double slit, obviously we've got slits. So S is going to stand for our slit spacing. No, it's not. That's wrong. Try that again. S is going to stand for our fringe spacing. Spacing is the key word here, not slit. So when we get these fringes, which are going to be displayed as bright and dark patches on your screen, the space between each of those is going to be your fringe space in S. Then we've got two more distances. We've got a small distance, which is a distance between the slits. Small distance gets a small d. Then we've got a big distance from your source to your screen, which is going to get a big D. And finally, we've got wavelength, which we already know and we're familiar with. Right guys, I'm back in and we're going to continue with waves. Right guys, I'm back in and we're going to continue with waves. So next we've got the Doppler effect. So this is mostly just the Doppler effect for light, and we can tell it's Doppler effect for light because we've got this c again. Our c is our speed of light in a vacuum. Now this is great, this is nice and easy. if you're doing high level, you've also got the Doppler effect of sound, which is different because sound has a medium, but light doesn't travel through a medium, it just travels through space. So we've got different equations for different Doppler effects for different things. Now, V is going to stand for the speed at which our source is moving. We've got delta F and delta lambda, which is change in frequency or change in wavelength. And then we've got wavelength. Now, the tricky thing about these questions is you won't get given the change in frequency or change in wavelength. You'll be given one wavelength, then another wavelength. And you've got to find the difference between those two wavelengths to get your change. And that's all the trickiness to it, really. It's not too hard, that one. So let's move on to topic D, fields, which some say is the hardest topic. So gravitational fields, we've got Newton's law of gravitation. And when we're looking at Newton's law of gravitation, let's look at this and how it's different to other ones. Here we've got M1 and M2, but other times we get a lowercase m and a capital M. Well, the reason for that is because they're both different scenarios. M1 and M2 implies that we've got similar masses. So here I'm using that law when I've got two astronomical bodies, a moon and an earth or something, orbiting around each other. Newton's law of gravitation is great for that. Then when we look at the laws we've got underneath, which is basically just rearranged versions of it, but a bit simpler. We've got capital M and lowercase m. Lowercase m is going to stand for the mass of our object, which is falling through a gravitational field. And uppercase M is going to stand for the mass of the object which creates the gravitational field, typically the mass of your planet or the mass of your moon. So the top one, we're talking planets, moons and suns. Bottom one, we're talking just things falling on a planet. Electric and magnetic fields. Now, it's important to understand differences here because they apply differently to different situations, and we can really compare them to the gravitational equations that we just looked at. So the first one, Newton's law of gravitation, is similar to whose law is this one? Who does this one? Coulomb. I think this one was named after Coulomb's law. Now again, we've got two Q's, two charges, that's what Q stands for. And as with Newton's law, we want to consider these as point charges. Newton's law, we're considering our planets as point masses, meaning that we're simplifying the situation and we're just imagining that all of the mass acts from one location at the center of mass or one location at the center of our charged body. And all we really need to know about that is then how we consider that with the radiuses. So imagine you've got a big planet, there's another big planet. If we want to get r, the radius of the orbit, we don't take the distance from one planet to the other from the surfaces. That would be wrong. We take the distance as if we imagine them as point masses. So they only exist in the point of the center of mass, which is the center of planets. And the distance from the center to the center would be r. Same is true for any charges. Oh, and look, we've got another k here. Physicists love k. This is in your formula booklet. It's a constant. You can figure it out. And then we've also got what it's actually equal to. And we have, I think k is called the Coulomb constant. You'll find that in your formula booklet. And epsilon 0 is our permittivity of free space. This is a measure of how much electric fields can pass through free space. Free space being a vacuum or air, because air is close enough to a vacuum. It's fine. So, All of that just to figure out the force between two objects. And if we imagine these two objects, you might be questioning yourself, well, is the force from object 1 to object 2 or object 2 to object 1? Like, are we talking about the force pulling that one that way or the force pulling that one that way? It's both. This is an example of Newton's third law. For every action, there's an equal and opposite reaction. So both of the forces are going to be the same size, just in opposite directions. So next we've got a equation for E, and this is quite similar to an equation just above it. So before we had little g is equal to F divided by M. Now little g is our gravitational field strength, or our acceleration due to gravity. If we think of it like gravitational field strength, well, this is kind of the equivalent. Instead of force divided by mass, we go force divided by charge, because this is all to do with charges. E here stands for our electric field strength, not energy, electric field strength. I know we use E everywhere, but that's the way it is. And electric field strength is given in the force per unit charge. Just like we can also give our gravitational field strength in force per unit mass. Now, we've just been talking about the electric field strength, and that equation you can use whenever you want. It's really useful because it basically just defines electric field strength. It's the force felt per unit mass by a positive test particle. And it always has to be positive because we have to decide at some point if it was positive or negative. And a test particle basically means that it's so infinitesimally small that it doesn't really affect the field around it. But we do have another equation for field, but this is field in a very specific situation. This is the electric field between two parallel plates. So you'll have seen this on an exam before. You've got one plate which is positively charged and one which is negatively charged, and there will be a field between those two plates. Now this field is uniform, so I can draw all of my field lines exactly the same distance apart. If I want, I can make the ones on the edges curved, for those extra fancy bonus marks. But everything else is perfectly parallel, same distance apart, to represent uniformity. And because we've got a uniform field, that means it's the same anyway. If I measure it, say here, it's going to be the same as here and here and here, which is handy. That means we can probably find an equation for it. Oh, there it is. This is our equation for it. Electric field between two plates is equal to the potential difference between the plates, that's V, divided by the distance between those plates. It's a nice, simple, useful formula. If they want to make it a bit hard, they'll ask you for, what would they ask you for? No, we're not going to get into that. Not got enough time because we're going through a quick examination of all of these, which takes us to magnetic fields. So, again, these are for very specific situations. Understanding the situations when we can use them helps us know when to apply them. And we can tell what they're for basically by all the letters in those formulas. So let's look at the first one. Q, I'm hoping Q is going to come quite easy to you now. That's charge. And then we've got V. It's a lowercase v, and we've seen that quite a lot before. Lowercase v is going to be velocity. And then we've got B, first time we've seen this, and B obviously stands for magnetic field, B for magnet. And then sine, and we've got a theta. The theta is going to represent the angle between the two vectors that we've got there. Velocity is a vector, and magnetic field is a vector. Any field always has a direction and a size. So if we see the vector for the magnetic field and the vector for the velocity, we can find the difference between them in terms of angle, and that will be our theta. And I've drawn there a nice 90-degree angle because that's the one we see most often. And sine of 90, any prizes? Know what it is? It's 1. So if we have that, that's when we have the maximum force between acting on our charged particle. Oh, I gave it away. It's a charged particle. Anyway, we know it's a charged particle moving through a magnetic field because we've got the magnetic field, we've got the charge, and we've got this velocity. The velocity is, of course, referring to the charged particle. And since we're talking about 90 degrees, let me remind you of Fleming's left-hand rule. That could come up in your exam. And let's explain how this could be applied to a charged particle. Now, when I get my students to remember Fleming's left-hand rule, I always get them to go like this. It's super cringy. Freeze. FBI. And they do that because the letters for your fingers go FBI. Force for F, B for magnetic field, I for current. Always keep every finger at right angles to the other fingers. If you do that, then you're golden. If you have like a limp kind of hand like this, it's never going to work. But this is a bit tricky to use with a charged particle because I talked about I, the current. Whenever we talk about current, we talk about conventional current. And because all the stuff to do with current was discovered by some French bloke 200-300 years ago, he didn't even have an ammeter. Like, he literally grabbed hold of one wire, grabbed hold of another wire, and see how much pain he felt to measure the current. He didn't know what electrons were. So he said, I think current goes this direction. He was almost right, it actually went that direction. And we've just kept this story, this lie of conventional current going one direction when it actually goes the other direction for the past 200 years. Because it doesn't really matter, actually. Like, it's not super important which direction it is. We can still make loads of really good predictions, and the models still work really well. And it's actually a bit of a pain to change things once you've been using them for this long. So fundamentally, my point is, conventional current doesn't go in the same direction of flow of electrons. Conventional current is defined as the flow of positive charge. So we imagine that that's how current in a circuit works, even though it doesn't. It still gets us the answer most of the time. I'll bring that back to particles. If current is a flow of positive charge, you can point this in the direction of any positrons or protons which are moving, because that's positive charge flowing. But if you've got an electron and you're trying to figure out how that relates to the current, well, electrons flow in the opposite direction to current. So if you see a charged particle moving through a magnetic field, and that charged particle is an electron, then you want to point your current finger in the opposite direction of the velocity of the electron. Isn't physics easy? I'm kidding. I wish it wasn't like this. I wish we just, changed things. We could have, but we didn't. So that brings us to the next formula. Again, let's think, what does this all mean? We have got B, again, magnetic field, current. Oh, hey, current. That means we might have some wires there, maybe. And then length. Oh, maybe L is like the length of the wires. Yes, you're absolutely right. This is where we get the proper Fleming's left-hand rule, because we've got the FBI. This is the force on a current carrying wire. So there we just got to think about, well, what's our sign in this case? Sine theta. Well, that's going to be the angle between the two vectors that we've got. Which ones do you think are the vectors? The magnetic field, the current, or the length? Length's a scalar, it's just how long something is, it doesn't have a direction. Current can go positive or negative, it can go one way or the other, so that's a vector. A magnetic field, again, we always put arrows on it, so that's a vector. So theta is going to be the angle between the magnetic field and the current. Again, when theta is 90, that will be when sine 90 will be equal to 1, and that's when we'll have our maximum force. Next we have the force per unit length. And then we've got all these other symbols. We've got I1, I2. That's two currents. Maybe there's two wires. And then we've got mu 0. Mu 0. This is the permeability of free space, different to the permittivity of free space, because it's not assessing how well an electric field can travel through air or a vacuum. It's assessing how well a magnetic field can travel through a vacuum or air. Very similar concepts, but different numbers. It's in the constant part of your formula booklet. And then we've got 2 pi, and then r. R is going to represent the distance from one wire to another. So if I've got two wires, current flowing through them, the distance between those two wires is going to be r. Right. Gonna skip the higher level stuff. And then we are on to nuclear and quantum. Not far now, guys. I think this is going to be the last one. So we've got the structure of the atom. E is equal to HF. This is a super powerful equation. It's all to do with photons. Right. The idea being that Einstein was it Einstein? Was it Planck? No, it wasn't Einstein. Einstein didn't like this. Planck didn't like the idea that photons were just, when light was just a wave, because we had lots of evidence that it wasn't a wave. It sometimes behaved like a particle. So then we thought, well, waves transfer energy from one point to another, and light does that. So then surely there must be some small bit of a photon which is transferring a small bit of energy. Well, that's what this equation is all about. E is going to tell us the energy of an individual photon. It is completely dependent upon its frequency. And that's it. H is a constant. That doesn't change. So the energy of a photon is not dependent on it. And basically what this tells us is the energy of a photon is directly proportional to its frequency. Higher frequency, higher energy. That is going to be a super easy equation to use. Sometimes you won't be given its frequency, but you'll be given its wavelength instead. That is not a problem. You already have the wave speed equation, which will help you transfer from frequency to wavelength, as long as you know the speed of the wave. And yeah, we're still treating the photon as a wave a bit, because it's both a wave and a particle. And whatever photon we have, if it's gamma rays, radio waves, microwaves, we know the speed in a vacuum is all the same. It's always the speed of light in a vacuum. 3 times 10 to the 8, it's in the constant part of your formula booklet. So, next we have E equals mc squared, Einstein's lovely equation. Now remember when I said it didn't really matter so much about the masses of neutrons and protons? They were so close together. Here is where it matters. Because here a tiny bit of mass can make a lot of energy. Because we're going to times that tiny bit of mass by the speed of light squared. And the speed of light squared is actually a pretty big number. So to do this, we generally find something called the mass defect. If you imagine something happens in your nucleus, a proton changes to a neutron or vice versa. I can't remember which way around it is, but basically some of the mass has changed inside that nucleus. Basically, some of the mass has changed inside that nucleus. So what we're going to do is we're going to find out what that change in mass is, bang it into this formula, and get ourselves a nice energy. The energy which you get will be in joules. So electron volts were basically invented because joules were a unit which was hard to work with, because scientists were like, I want to work with numbers like 1, 2, and 3, and 20, easy numbers I can think about. But when they were working with joules, they were working with like times 10 to the negative 19, which is hard to think about. And physicists like to make things easier to think about. So they said, let's make this new unit called the electron volt, which will be like maybe 13 or 2 or 20, some easy numbers to work with. So 1 electron volt is much smaller than 1 joule. And that's how I remember how to convert between them. I know they're linked by the elementary charge. But sometimes I forget if you have to times by or if you have to divide by. So because I know 1 joule is like a gazillion electron volts, if I do 1 joule divided by the elementary charge, which is 1.6 times 10 to the negative 19, dividing by a really small number gives you a really big number. So divide by there. Let's make that clear. That's divide by E. And then to go the other way, I'm going to times by E. On to the last one, guys. We are going to look at parsecs and parseconds, which is I'm going to say purposely confusing unit of distance to measure astronomical distances, because like the distances of stars and galaxies are vast, like humongous. Measuring them in meters would be mind-boggling and too hard. And do you know what? We can't even measure them in astronomical units. Like, I'll tell you what I mean by that. Because we've got the sun, and we got the Earth. Like, and if I wanted to have like 1 astronomical unit, I could take the distance from the sun to the Earth and call that 1 AU. But it turns out because space is so ridiculously big, that's not good enough. What we have to do is come up with this really complicated kind of idea, where we imagine we've got a star way over here, right, and then we look kind of towards that star, and we can kind of see what's going on behind it, and then we wait half a year. Yep, half a year, until the Earth's on the other side of the sun, and then we look at it again. We can get this kind of set up. If I take the angle that is in the middle there between that kind of dotted line and the line which we were viewing before, and I imagine that that angle is equal to 1 arcsecond, then the distance from the sun to that star, which we're hoping is going to be exactly there, is going to be 1 parsec. Like, we have to imagine this is going to be an extremely long distance, because this angle has to be 1 arcsecond. An arcsecond is kind of like a degree, but smaller, because we can split our degree up into 60 little chunks and call them arc minutes. 60 because it's a minute. And then we can take 1 arc minute and we can split that into 60 little chunks and call each of them an arcsecond. So this is an incredibly small sliver of an angle. And that's what that has to be there. 1 arc second. Now, this is a hypothetical unit that we can now use to measure things. But actually, if we know like this angle, which is produced when we measure the hypothetical star, some new star, this angle we could consider to be our P over here in arc seconds. And if we know that angle, then we can come up with this idea of how far away it is in parsecs. Once we have its distance in parsecs, we can use the formulas the constants we saw at the beginning of this formula booklet. The ones I said wouldn't be too useful. We can actually use this to convert into light years, and if we wanted to, we could then convert light years into meters. And that's about it, folks. That is all of standard level, done at a very quick pace, showing you everything you need to know about the formula booklet. It's a really powerful booklet. Like, there's so much useful stuff in here. And I've just realized I missed out all of B1. Well, I'll put it back in the end. It'll work in the edit. Anyway, thank you for joining me, guys. Good luck in your exams. I want you to know I've got every faith in you.